Last time we determined the energy eigenvalues for the hydrogen atom, and we wrote it in terms of a ground state or an E1 energy. If we want, let's compute the ground state energy. Now suppose n is equal to 1, so I need to compute this. When I do, I get a total of minus 13.6 electron volts, which those of you who had general chemistry recognize that as the ionization energy, the energy needed to pull an electron off of the hydrogen atom. What we call the binding energy of hydrogen, or the amount of energy one has to supply to ionize hydrogen, remove the electron. For the case of n equals 1, both L and m equals 0. Hence, we would write for that case psi of 1, 0, 0 is of theta, r theta, and phi is then going to be equal to r 1, 0 of r times y 0, 0 of theta, which of course is just 1 over 4 pi. R1, 0 is equal to A naught, the Bohr radius, over A times e to the minus r over A. And that's because the recursion formula terminates after the first term. We want to normalize the wave function. N equals 0 to infinity, r1, 0 squared, r squared dr has to be equal to 1. That's A naught squared over A squared integral e to the minus 2r over A. R squared dr gives me A naught squared over 4 times A is equal to 1. So A naught then is equal to 2 over the square root of A. Y 0, 0, of course, as we said, is 1 over square root of 4 pi. And so we put it all together. Psi of 1, 0, 0 is equal to 1 over the square root of pi A cubed e to the minus r over A. How about the first excited state? Well, the first excited state means n equals 2. That's going to give me an ionization energy of minus 3.4 electron volts. And now L can be either 0 or 1, and M can be either 0 if L is 0, or minus 1, 0, or 1 if L is 1. And we can obtain all the rest of them as we want to. The total degeneracy of each energy level then is just n squared. That's how many eigenfunctions would correspond to the same eigenvalue. By the way, if you remember, we were talking about, we have this polynomial v of rho. We can write it in the following way. Capital L of n minus L minus 1 to the 2L plus 1 of 2 rho. That's a well-known function. This is what we call the Laguerre polynomial. So, or we call actually the associated Laguerre polynomial. Such that L of q minus p to the p of x is equal to, or is defined as, minus 1 to the p d dx to the p LQ of x, where LQ is the Laguerre polynomial. So if we'd like to, we can write the complete normalized hydrogen wave function. Psi of of n, L, and m of r, theta, and phi as square root. My normalization constant is huge. 2 over NA cubed, n minus L minus 1 factorial divided by 2n, n plus L factorial cubed e to the minus r over na, 2r over na to the l times l n minus l minus 1, 2l plus 1 of 2r over n a ylm of theta and phi. That's ugly, but it's exact. It's one of the few exact things we have in physics. Extremely rare. But that is the solution to the Schrodinger equation in 3 dimensions for the hydrogen atom. We assume the atom would stay in its stationary state forever. However, if it encounters some perturbation, it may be raised to an excited state. Then, of course, it will eventually return to the ground state, give off a photon of energy that's equal to the energy difference between the ground state and the excited state that it's in. So this is it's a really great result. It's sort of, as I say, the gold standard for anything that you want to use in place of quantum mechanics, although we tend not to do that. But it had better solve the hydrogen atom if you're ever going to replace quantum mechanics with something else. So we're going to stop with that. Next time we're going to move again in 3 dimensions, but we're going to discuss angular momentum in a great deal of detail. See you then.